Hi! In this video we present some ideas about the notion of parametrization of surfaces. There are a lot of tools to study surfaces, and again, as in the case of curves, we can work with many mathematical tools. Tools from differential calculus, parametrizations, algebraic tools, taking advantage of the properties of polynomials, or numerics, doing approximation of surfaces, among others. We will center our attention on the differential tools. The idea in this case is to generalize what we have done with curves. When we parametrize a curve, we begin from an interval or the real line. Now we have to start with R2, the plane, or a subset of it. In this example, we start with a map, as in the image, and we want to describe certain information of the region we have chosen. It could be, for instance, its height from sea level depending on how far we move north-south and east-west from a given point in the map, considered the origin of the map. That is an appropriate reference system for all the points of the region. That region was a subset of the plane. Formally, we define a parametrized continuous surface in R3, the space, as a continuous map from a set D contained in R2 to R3. Eventually, D can be the whole plane R2. The variables of this set D are usually denoted by T and S respectively. And we have a relation between the values of the variables T and S and the points of the space. And taking into account the coordinates of the points of the space, we have the relation shown on the screen. In the case of curves, we recall here that a parametrized surface and its trace are not the same. A parametrization provides a trace, but given a trace, we don't recover the parametrization. But why is it important to work with parametrized surfaces instead of their traces? The parametrization is a function that is usually expressed as a combination of elementary functions, polynomials, square roots, trigonometric functions and their inverse, exponentials and logarithms. Then we can take advantage of the many properties we know of these functions. But even if we consider combinations of these functions only, the surfaces and their traces can be very complicated. We strongly recommend the use of interactive geometry software as GeoGebra, or Maple or Mathematica or any other appropriate software. We begin now to show some easy examples of parametrized surfaces. For instance, the plane, a flat surface containing all the lines that connect any points of it. Its parametrized expression is now on the screen. It is in terms of two vectors, v and w, and a point called P. Here we have an example with a particular point P and two particular vectors. Another example is any cylindrical surface. This surface contains all the straight lines with direction any given vector v, with components v1, v2 and v3. These lines pass by all the points of a given space curve alpha with components alpha1, alpha2 and alpha3 of t. The parameter S is the one which provides the different points of the lines. If it just moves along a finite interval, we have segments of a given length instead of whole lines. In this picture, we see the Cajasol Tower at Sevilla, Spain, with cylinder shape. Or this other cylinder with equation x squared plus y squared equals 3, which contains all the straight lines with direction 0, 0, 1, that is, all the vertical lines. These lines pass by all the points of the circle of center 0, 0 and radius the square root of 3. The parameter S is in the real line and the parameter T between 0 and 2 pi. Another example is the surface of revolution. We give here the parametrization of the surface obtained by rotating the curve alpha with components alpha 1, alpha 2, and alpha 3 of t around the z-axis. As an example, we can take a sphere, like that one at the Bristol Planetarium. The sphere of center 0, 0, 0 and radius 2 can be parametrized as the rotation of the semicircle illustrated in the picture around the z-axis. Then we obtain the expression that now we have on the screen. In the case of curves, we can see the graphs of continuous functions, now depending on two variables, as parametrized surfaces. It is enough to set x equals t and y equals s, and the third component will be a function f of x and y, that is, a function of t and s. On the screen we have the graph of a function, the trace of the surface parametrized as the last equation on the screen.